Okay, so today we will go over superposition first of all, and then superposition, the idea of it is to solve any circuit that has two or more sources. In our case here we have voltage sources. And then before we go into that, how did we used to solve this from before? We used to use nodal. How did we do nodal? Nodal, we used to set a voltage V here, and then we had a ground over here. We would set our ground voltage. Ground voltage basically means V0, which is equal to 0 volts. And then we will start applying KCL at this node. The node in the middle here, we're going to apply KCL to it. So what was KCL? KCL means all the current entering is positive or negative, depending on how you guys want to define the direction. Just stick with one direction. So I usually say entering is negative and exiting is positive. Okay? And then you assume a direction for your current. So let's say we have a current going out from here. This is I1. And we have a current going out from here. We'll call this I2. And then we have a current going in من هني. We'll call this I3. All right. So this is just nodal review. I'm just reviewing nodal analysis as سريع. And then I will show you how to do it, solving the same exact question using superposition. So nodal, what did we do? We used to apply KCL. So negative is for entering and exiting is positive. So we're looking at this node. If we look at this node, we can see that this current is entering, so I1 is going to be negative, I2 is exiting, so it's going to be positive, and I3 is entering the node, so it is also going to be negative. So if we want to write our equation, we're going to write minus I1 because it's entering, plus I2 because it's exiting, and minus I3 because it's entering, and this is all going to be equal to 0. And then what did we do? We just used our basic V equal IR equation. In other words, I is equal to V over R for each specific current. So we can substitute back into the KCL equation. We had our I1, which was minus I1. Then we have our plus I2. Then we have our minus I3 equal to 0. So how do we do that? So first of all, we have defined that this is our ground. This over here is our ground voltage. So we know that this is 0 volts. If this is our ground, here we have a gain of plus 12 because of this voltage source on the left. So it is going to be plus 12 over here, volts. And here we also have plus 16 since the bottom is ground. So the top is going to be plus 16 volts on the right side. Tamam? First thing we do is we have to define or identify polarities of each resistor. So we have plus minus since current is entering from the left side here, plus minus like this for this resistor since current is entering from the right side, and plus minus like this for the resistor in the middle from up to down because current is going from up to down. And then we just apply. So first of all of these are going to be divided by the resistances because I is equal to V over R. So for the first one, for I1, the resistance is 470. So 470 is going to be down. For the second one, it's going to be 200. هو resistor for I2. And for I3, it is also 200, which is the resistor up here. All right? So this is the first step. Now we just have to put in our voltages. How do we put in the voltages? We are going to look at, first of all, let's look at I1. So for I1, whatever is on the plus side is going to go first, and then we're going to subtract whatever is on the minus side. So on the plus side, we have the 12 volts. So this is 12. And on the minus side, we have our V, our nodal voltage, which we need to find. So it's going to be minus V. All right. Again, what I did is, depending on the polarities of the resistor, from plus to minus where current is flowing. So on the plus side, we have plus 12 volts. And on the minus side, we have our V. That's why it's 12 minus V. We will apply the same thing again for I2. So on the plus side, we have V. All right. So this plus side here, we have our V. And on our minus side, we have V0, which is simply just 0 volts. So we can just write it as minus 0. Tamam? And the same thing we're going to do for I3. So I3 on the plus side, we have our 16 volts on the plus, and on our minus side, we have our V, so it's going to be 16 minus V. So it's going to be 16 minus our V, nodal voltage. Now we have this equation with one unknown. We can find the voltage just by simplifying this equation. If I do that very quickly, so we're going to have, if I distribute the minus here, it's going to be minus 12. It's going to be minus 12 plus V over 470 plus V over 200 minus 16V plus V over 200. So if I'm distributing the minus, to make it a bit clearer, this is going to be plus minus 16V, minus 16 plus V. Tamam? And this is equal to 0. And then you just solve for V. So if we want to make it easier, we just separate the fractions, but plus V over 470 plus V over 200 minus 16 over 200 plus V over 200 equals 0. We group the V's and we group and take it common factor, فبيكون V 1 over 470 plus 1 over 200 plus 1 over 200. Simply all I did was all the V values over here. I took V as a common factor, وبعدين ال 470, 200, and 200, or 1 over them. I just put them in brackets. And we'll take the constants to the other side, that's equal to 12 over 470 plus 16 over 470. Then now we can find our V is just equal to 12 over 470 plus 16 over 470, all divided by this whole thing, which is 1 over 470 plus 1 over 200 plus 1 over 200. إذا يعني you want to simplify it algebraically بطريقتكم الثانية, it's fine as long as your math is correct. So we're going to find out that V is equal to, if we put just this whole equation into the calculator, so it's 12 over 470 plus 16 over 470. دقيقة أحس في شيء غلط. It's 16 over 200. Yes. 1 second. 16 over 200. Sorry about that. Then, so 16 over 200. And we will divide all of that by 1 over 470 plus 1 over 200 plus 1 over 200. This is going to give us V is equal to 496 over 57, which is simply 8.70 volts. Now that we have found our nodal voltage, what do? We just take these equations again. So for I1, the idea is we wanted to determine الكرنتس لا نبغى نحصل I1, I2, I3. فشو اللي بنسوي؟ الحين حصلنا احنا ال V بنعوض حق كل واحد. So we know that this is I1, this is I2, and this is I3. Okay, so we're just going to use these equations once more to find our currents. So for I1, it is equal to 12 minus V over 470. So it's 12 minus, what is our V? 8.7 over 470. For I2, again, we're going to look at this equation. It's V over 200. So I2 is V, which is 8.7 over 200. And for I3, it is equal to 16 minus V over 200. For 16 minus V, which is 8.7 over 200. If I put all of these in the calculator real quickly, so I1 is going to be equal to 12 minus 8.7 divided by 470. I will get 7.02 milliamps. And then I2, 8.7 divided by 200, which is 43.5 milliamps. And then I3 Again, 16 minus 8.7 divided by 200. It's going to be 36.5 milliamps. To double check if your current is correct, you just plug it into this equation, the KCL equation. So it's going to be minus I1 minus I3 plus I2, and they have to be equal to 0. And this is how you find your current for each one. Last thing, if they're asking you to find voltage drop, you have already calculated the voltage drop for each resistor, which is the top part of each of these equations. This is your voltage drop. فإذا تبون تحصلون voltage drop, for example, for I1, it's simply 12 minus 8.7. Voltage drop for I2 is 18.8.7. And voltage drop for I3, which is يعني VR3, is 16 minus 8.7. Because remember, all this equation is simply just I3, for example, is equal to VR3 divided by R3. All right, because VR3 is equal to I3 R3. Ohm's law. Tamam? So if you want to find voltage drop, it's the top part. This, we've already done it a lot of times. يعني finding currents using Nodal. And this is one method of solving. So for the exact same circuit, we can solve it again now using superposition. And then instead of Nodal. Superposition is simply just another way of solving this. It's just a different method of solving this for when you have more than one voltage source. So let me just copy paste this down here. So now if we want to use superposition, okay, so this is now superposition. Let's keep our assumptions the same. Let's keep the current assumptions the same. Let's say I3 is assumed to be upwards, I2 is assumed to be downwards, and I1 is assumed to be upwards. The very first important step is make sure you know your directions. I1 up, I2 is down, and I3 is up. And we will talk about that in a bit later on when we look at how we are solving. And then, so this is our assumption. We made the assumption of this. فعادي, if we get it as a negative value, we know that it has to be in the opposite direction. So it's fine. This is just our assumption. The difference now in superposition, the idea is we want to eliminate one source and solve the circuit using another source. For example, مثلا نشيل 12 volts, بعدين we will solve the circuit. And then بنشيل 16 volts, and then we will solve the circuit again. To see if, and then we were going to just combine both, and you will see how I'm going to do that now. So again, first step, assume your current directions and يعني identify them properly. Now let us look at the circuit again. First, we're going to eliminate the second source, which is the 16 source. So let's say source 1, which is the 12 volts. Tamam? This is our first one. So source 1, 12 volts. So we're only going to solve the circuit كأن بس عندنا موجود ال 12 volt voltage source. If I just copy paste this down one more time over here. And then what we're going to do is we're going to remove this source completely, the 16 volt source. And we're going to shorten the circuit at where it is. Tamam? So it's going to look something like this. Now this is a much easier circuit to solve. You can find the currents much easily here using a lot of different methods. Up to you which method you want to use from everything that we have learned so far. One more thing before I move forward. هو عادة, if you have a voltage source, you're going to shorten the circuit. And I'm not sure because I haven't seen this before with you guys, but in case, if you have a current source, okay, this is a current source, you're going to open the circuit. فبما معناه you will cut and open the circuit. But for now, we're just looking at a voltage source because I haven't seen any question with current sources so far. But just for your information, if you have a current source, you're not going to be shortening the circuit. You're going to be keeping the circuit open. Anyways, moving on. So now, let us assume our directions for current once more. So now we have a new circuit, so everything is changed, all right? So first thing, we know that this is one source, so we can have a good idea on where the current is flowing. We know it's going to be flowing out of the voltage source, and it's going to then try to return back to the voltage source. So we know that this is going to be going downwards, all right? We know that the current is going to be going upwards here. And then we know the current is going to be going in the opposite direction here. It's going to be going downwards as well because it's trying to come back to the source. Okay. Again, you can assume any direction you want. At the end, it just depends on the sign, and make sure you're following where the signs are and if it's up and down when you're combining them. So this is gonna change also our polarities. Actually, this polarity is the same. This is the only polarity is gonna change. So this is gonna be plus minus like this, and this is gonna be plus minus like this. And we're gonna name them something else. Let's call this IS1. Let's call this IS2. And let's call this IS3. Okay? So let's call this voltage source S, يعني بما معنى. All right? So this is our S voltage. All right? So IS1, IS2, IS3, we can find the current in any way you want. You can either reduce the entire circuit and find S1. You can do mesh method, loop method, whichever you are more comfortable with. We are no longer doing nodal, so we don't care about the nodal voltage. So me personally, I usually prefer reducing the circuit or applying mesh. Up to you guys how you want to solve this. Me, in my case, I'm just going to do circuit reduction. So again, if we are looking at the circuit, we know that this resistor and this resistor are in parallel. How do we know that? Because they're connected at 2 points. All right. So these two lines, okay, معناته these two are connected in parallel. So we're going to reduce these in parallel. And then we know that this is connected with them at 1 point. So it's going to be in series with them. All right. I'm obviously just doing shortcuts here because you guys should be able to reduce the circuit by now. So if I want to find R total, it is simply going to be equal to these two, which are in parallel. So it's going to be 200 times 200 over 200 plus 200 plus the series connection with this resistor here, which is 470. So this is going to be equal to 570, if I'm not mistaken. Let me just double check. 200 times 200. Yep, it is 570 ohms. Okay, so now we have found our total resistance. When we find our total resistance, the circuit is going to look something like this. All right, plus minus, this is our 12-volt source. This is our R total, which is 570 ohms. And this is our current I total, or it's the same current, which is IS1, and it's the same current leaving the voltage source. So these two currents are the same. All right. So now we can find IT, which is IS1. They're equal to each other. So IS1 equal to IT is equal to simply V over R total, which is 12 over 570. IS1 is going to be equal to 12 divided by 570, which is 0.02105 amperes, or it's 21.05 milliamperes. Okay, and it's very important since this is a positive value, so معناته the assumed direction is correct, so we have to put the direction as up. Right? It is very important to mention the direction so you guys don't get confused later on. Now that we found our total resistance or the first current, we can now find the other two currents in any method you want. Usually the method I showed you guys is by finding VR1 and then equating and then doing all of that. But today I want to explain a new concept just in case you guys want to use it, which is the current divider rule. All right. So what is current divider rule? Current divider rule. When you have any circuit with two resistors in parallel, all right? Any circuit with two resistors in parallel, let's call this V, all right? And let's call this I total. We're going to have a current over here, I1, and we're going to have a current here, I2, okay? Let's call this R1, and let's call this R2, tamam? So you know already how to do it using voltage and VR1, VR2, but this is a shortcut method if you guys prefer. You don't have to use this if you want to use the old method I usually use. I prefer using the old method. I hate using current divider rule personally, but I want to explain the concept just in case you guys want to use it. So you have an equation. Let me just grab the equation so I don't mess up with the equation as well, because I don't use current divider rule a lot. So you're going to have this equation that you can apply. Okay. This is the equation that you can apply. So I1 is going to be equal to I total, which is the current entering the two parallel resistors, times R2, which is the other resistance, over R1 plus R2. Okay, so this way you can find I1 directly, as long as you have the total current. And the same thing for I2. So I2 is going to be equal to I total times R1 over R1 plus R2. Keep in mind, these are the opposite ones. So if you're finding current I1, بتستخدمون R2 up there. If you're finding current I2, you will put R1 up there and you will multiply it with I total. All right. So this is one way of solving it, current divider rule. So in our circuit here, we can apply that current divider rule in the exact same way, because if you notice here, then we have a current IS2, we have our I total, we have a current IS2, and remember, these two are in parallel. These two resistors are in parallel, okay? So IS1 is our I total, and we can find our IS2, اللي هو هذا current, which in this case I called it I1, but in IS2, if I want to write the equation for it, IS2 is going to be equal to I total, and then the second resistor, in this case, they're both equal resistors, 200 ohms. But again, this is this resistor, all right, divided by 200 plus 200, okay? And for IS3, it is equal to I total, again, 200 over 200 plus 200. It makes sense. These currents have to be equal to each other because there are equal resistances, okay? But this is how you would apply current divider rule if you want to find, if you want to use the shortcut method. Me personally, I don't like using this rule. Sometimes I confuse myself. Sometimes I forget what's up, what's down. I'm going to now continue solving. I just wanted to explain current divider rule, but I'm going to continue solving the usual way I solve it, using polarities, using voltages. So we know that we have 12 plus 12 volts up here, صح? So we want to find voltage here. We need to find this voltage V. Let's call it V, okay? How can we find this voltage V? We know that this, let's call it VR1, is equal to 12 minus V. تمام? Another equation, also VR1 is equal to IS1 times R1, Ohm's law. And then, so we can find VR1 here, and then we can find our node voltage using VR1 equation from here. So if we simplify this, IS1 and R1, so IS1, we found it earlier, which was 21.05 milliamps. Of course, you're going to put it as amps when calculating. So it's 0.02105. So 0.02105 times resistor 1, which is 470 ohms. So now we have found our VR1 to be times 470 to be 9.89 volts. And then, so we know that this is going to be equal to 9.89 volts. Let me just put this down so that there is no confusion. So it's going to be like this, all right? So now we can find our V. It's equal to, we just take it to the other side and take the 9.89 back. So it's going to be 12 minus 9.89, which is 2.105 or 11 volts. Okay, so 2.11 volts. Now that we have found this voltage over here, we can find the current through each one using the same exact method. We know that VR2 is equal to IS2 times R2. We also know that VR2 is going to be equal to, the positive side is V, the negative side is 0, so it is equal to V over 0. So it's going to be V minus 0 over R2. All right? صح? No, what am I saying? Sorry. V minus V0, that's it. It's V minus V0, which is 0. V minus V0. تمام؟ we know that V is 2.11, so we know that VR2 is also 2.11. So now we can find the current using this equation. So IS2 is equal to VR2 divided by R2, which is 2.11 volts, over R2 is 200 ohms, which is equal to 2.11 divided by 200. That is 0. Let me write it this way, عشان later on we can refer to it. Therefore, IS2 is equal to 0.01055 amperes, which is equal to 10.55 milliamperes. Then, again, direction is important. Since we got a positive value for the current, we know that our direction is correct, so we have to write down. Tamam? Same thing we're going to do for IS3 now. So IS3, we know that VR3 is equal to IS3 times R3. And we know that VR3 is equal to, again, same idea. It is the voltage here, the positive side, minus the negative side, which is the ground voltage, which is 0. So it is equal to V minus 0, which is simply equal to 2.11 volts again. Therefore, IS3 from the first equation here, we know that IS3 is equal to VR3 divided by R3, which is equal to 2.11 over 200. So IS3 is equal to 0.01055 amperes, or it's equal to 10.55 milliamperes. Again, direction is important. Assume direction is downwards. So we're just going to write down. Tamam? This is, now we found the current for just the first source, source 1. All right? We will repeat the exact same thing again now for source 2. And then we are going to eliminate source 1 and we're going to solve for source 2. So let me just copy paste this down one more time. So now we are going to be looking at source 2. Okay, so source 2, which is the 16-volt source. Let's call the source P. All right? So we can avoid confusion. So now we are going to remove this. Since this is a voltage source, we're going to shorten the circuit. Okay? This circuit is shortened. Again, current directions are all going to change once more, depending on the new circuit. And we have one voltage source now only. So same exact method again. So 16 volts, we know it's going upwards. So the current has to leave from the positive side, يعني. And then, so we know that the direction of this one, let's call it IP3. All right, it's going upwards. It's going to the voltage, going to this point, and then it's going to be going downwards here, and it's going to be exiting in that direction and going downwards here as well. We'll call this IP1, and we'll call this IP2. All right, it's very important you name the currents the same يعني sub number. يعني هنا احنا سمينا high current 1. And all of them, it is the exact same location of that current. So this is I1 down here. In the original circuit, this is I1 as well. And in both superposition, this is I1. So you don't get confused later on when you are combining all the currents. فالحين, we do the exact same thing again. If you notice, these two resistors are in parallel with each other. First of all, let me fix polarities really quickly. This is going to be plus minus like this. So this and this circuit, this and this resistor, sorry, they're in parallel because they're connected at 2 points here and here. So we can reduce them together as parallel, and then they are in series with this circuit over here, or sorry, this resistor over here. Our total is equal to 470 times 200 divided by 470 plus 200 plus the series, which is the 200 ohm resistor over here. So put this in the calculator real quick. So 470 times 200 over 470 plus 200. all of it plus 200 is going to give me 340.30 ohms. All right. So this is our R total now. Now that we found our total, we can find I total. Now keep in mind, if we redraw the circuit, عشان بس it's clear. So we have this is our voltage source. And this is our resistor, our equivalent resistor R total, which is 340.30 ohms. This is our 16 volt source. Now, if you notice, what current is coming out of it, it's IP3. So I total here, I total is equal to IP3, right? This is the current. And to find IP3, so I total equal IP3, which is equal to V over R total, which is 16 volts over 340.30 ohms. Therefore, IP3 is going to be equal to 16 divided by 340.3, you get 0.04702 amperes. Or if you want it in milliamperes, it is 47.02 milliamperes. Again, direction is important since we got it positive. The direction is upwards, so we have to write up. Okay, so we found our IP3. Again, you can use current divider rule if you want to find IP2 and IP1. For me, I prefer not to do that, but there's nothing wrong with using that. So if I just copy paste the circuit down here one more time, plus minus. So here, if we are looking at R1, so VR1 is equal to, or sorry, this is R3. So VR3 is equal to IP3 times R3, which is equal to, we have IP3, which we found, which is 0.04702 times R3, which is 200. We find out that VR3 is equal to 9.40 volts. All right. So now, again, we also know that VR3, depending on polarities, again, this is plus minus. So from plus to minus, so the plus side is going to be 16 minus the negative side is V. So we can find out, and we know that this is equal to VR3, which is 9.4 volts. So we know that V is going to be equal to 16 minus 9.4, which is 6.60 volts. All right. So now that we have found our V, again, repeating the same steps as we did earlier, nothing new. We're going to find IP2 and we're going to find IP1. So let's start with IP1. So if we're talking about IP1, we need to talk about VR1. VR1, the voltage drop across the first resistor, is going to be equal to IP1 R1. R1, we need to find IP1. So another equation is, we're going to look at the voltages here. So this is plus minus, so it's V minus 0. So it's V minus 0. Why is it V minus 0? Again, we have V on the positive side, and on the minus side, this is just the ground voltage. All right, so it is 0. That's why it is V minus 0. So VR1 is simply equal to 6.6. Let me put this down actually like that. Okay. So 6.6 volts. Now we know that if we rearrange this equation, IP1 is equal to VR1 over R1, which is equal to 6.6 over 470 ohms. All right. Therefore, we know that IP1 is going to be equal to 6.6 divided by 470, which is 0.01404 amperes, or in milliamperes, it's 14.04 milliamperes. Again, since it is a positive value, that means our assumed direction is correct, which is downwards. So we're just going to write down. Okay. Again, we're going to do the same thing for VR2. So VR2 is equal to, if we look at VR2 over here, this is the positive side, and 0 is the negative side. So it's again V minus 0. So it's V minus 0, which is equal to 6.6, was it? Yes, 6.6 volts. VR2 is equal to IP2 times R2. IP2 is equal to VR2 over R2. معناته 6.6 over 200. Therefore, IP2 is equal to 6.6 divided by 200, which is 0.03298 amperes, or in milliamperes, it's 32.98 milliamperes. Again, since we got a positive value, معناته the assumed direction is correct, and IP2 is assumed downwards, therefore it is down. If, for example, we get a negative, this is just it for example, if we got a negative value here, we know that our assumed direction is incorrect, so we have to reverse the direction, and we would write up instead of down here. This is if we got a negative value. Yani we will remove the negative and we'll write up instead of down. This is the idea. However, in this case, لأن كله قاعدين يطلعون positive, معناته the assumed direction is correct. This is, now we have found the currents for each source by itself. For source 1, over here, source 1, we have found our currents, which is IS1, IS2, and IS3, which we did over here. And the same thing for the other one. So let me just bring these all down. زين عشان بعدين we will look at them together. So this is for the first one. Let's keep everything in milliamperes for now. Okay, IS1, IS2. Okay. Again, we'll just keep everything in milliampere. And IS3. Again, it is very important to make sure your directions are correct. If you make a mistake in the direction, your entire solving will be incorrect when it comes to superposition. تغيير في الجهة تكون بس في اللي نشتغل عليه صح لو كان سالب. Yes, يعني for example إذا إحنا قاعدين نشتغل على source 1, okay? So this is source 1 where we're working here, and then we're working only with these directions. ولا شيء ثاني. We don't care about the source 2 superposition or the entire circuit. We are only looking at this one, at this circuit. So for example, let's say we got IS1 equal minus 5, whatever. زين معناته the direction assumed here is incorrect. So معناته we have to put it as a positive value going downwards. We would say IS1 is 5 down. This is what will happen. Just IS1. ما بيأثر على هني assumed in the beginning ولا بيأثر على the one for circuit 2, for this one, for source 2. All right? It will not affect it at all. So again, I'm going to do the same thing here. I'm going to get all the sources that we found earlier, all the currents, sorry, that we found earlier. This is IP3. Up, and then we found IP1 and IP2 over here. All right. And IP2. Usually, I recommend doing a table. Usually, I would recommend doing a table. But it's up to you how you want to solve this. Then making a table sometimes takes time, but usually I prefer building a table as I do not get confused for when I want to combine them. الحين, this is where it is very important. Now we need to go back to our original assumed directions. Remember when I told you the very first thing you do is you assume your directions, which is up, down, and up in this case. زين? Because now we are going back to the original circuit. We want to relate this to the original circuit. All right? So this is our assumed directions. Okay, so we have to look at the direction that we have for I1, and this should be the same as this direction. If not, then it will be negative. For example, let's start with I1. So I1 is up, okay? IS1 is also up, so it is going to be a positive value because it's in the same direction that is assumed, milliamps. IP1 is down, so it is going to be negative because this direction over here is opposite to the assumed direction for the original circuit. That is why it is going to be negative. معناته بيكون minus 14.04 milliamps. You put this in the calculator and you will get your final value for I1. You will do the exact same thing again for I2. So originally the assumed direction I2 is down. معناته if you get a down value, it is going to be positive. If you get an up value, it is going to be negative for I2. So again, we'll do the same thing. So here we have down, so it is positive 10.55 milliampere. This is also down over here, so it is plus 32.98 milliampere. And you're going to get your final value for current 2. And now current 3 is equal to, again, we have it as up. So if it is down, this is going to be a negative value. This is up, so this is going to be a positive value. And therefore, this is going to be minus 10.55 milliampere plus, because this is up, 47.02 milliampere. And if you just plug all of these into the calculator, you get your final current value. Any questions about superposition so far while I fill out, while I just do the calculations real quick? This is going to be 7.01 milliamp plus, this is going to be 32.98 plus 10.55 plus 43.53 milliamps. And this is going to be 47.02 minus 10.55, 36.47 milliamps plus. So again, if you notice here, we got positive values for all of them. زين؟ لأنه we got positive values معناته the originally assumed directions are correct. يعني a circuit, the very first circuit that we had, وين راح؟ هني, this original circuit, we had assumed directions on it. These assumed directions are correct. If not, معناته we're gonna have to reverse the direction. So we can say, in this way, we can say that I1 is 7.01 milliamp up. I2 is 43.53 milliamp down. And now we assumed it down and it's positive, so it's down. And I3 is 36.47 milliamp. And we assumed it up, so it is up since it is positive. And this is your final current for all of these values. Any questions about superposition? شوفوا, it looks long, it looks very complicated, but it just takes time to solve. It's not that difficult. يعني you guys have to know just how to solve any circuit in any way. You guys can use any method. يعني if you guys wanted to use mesh or loop method instead of the way I did it, it is completely correct. As long as you're eliminating one source, solving it, and then eliminating the second source, solving it, you are using superposition. This is the main concept of superposition. يعني you're going to be eliminating this source and you're going to be solving this circuit like that. Then you're going to be eliminating this source and solving the circuit like this. And then you're going to add up everything with directions, obviously, to know if it's positive or negative. And that is the concept of superposition. طبعا, in reality, this is because it's the teaching, educational wise, it's different. In reality, you will not use superposition when you only have two sources. فرضا, imagine you had here plus minus, imagine you had here plus minus, imagine you had here plus minus, imagine you had here, and you had a complicated circuit with a lot of voltage sources. And you only want to know the effect of this voltage source on the circuit. That's where you would actually use superposition in practical real life. However, here it is just going through the concepts. Lena, if you want to solve this using Nodal earlier was so much faster and we could have found it easy. But this is just to explain the concept and understand how to use or how to apply superposition. فعندكم any questions؟ خلاص واضح؟ Is it clear؟ Yes, no, maybe. عشان if it's clear I can move on with Thevenin يعني. يعني I wanted to solve شو اسمه but I don't think I'll have enough time. But I wanted to solve these two questions. This question is exactly the same, the one that is given in Moodle for superposition, exactly the same thing that I just solved. This one, similar concept, but Allahumma voltage source is here. All right. يعني if I just go through this one very quickly. زين. You guys are going to eliminate أول شيء هذا. You're going to eliminate it. So you're going to have a closed circuit here. You're going to notice that this is in parallel with this. This resistor is in parallel with this, in series with that. And then you're going to solve for currents over here, all the currents for VS1. Then you're going to eliminate VS1. You're going to have a short circuit here. You're going to notice that this and this are in parallel because they're connected here and here. And then you're going to just reduce and all of that. تمام? So Yani, this is the one. I already did the solution and I have uploaded the solution on the Discord server. But it's exactly the same concept. You guys can go through it just to see. Yani, هني you guys need to know not superposition. You guys need to know your basic reduction of circuits. You need to know your KCL, your KVL, how to apply them, and all of that. That's the main important thing. Just keep in mind when you're finding the superposition, when you're eliminating a voltage source, all right? So a voltage source, this will become a short circuit. يعني, if we have the voltage source here, we're going to just put a line between the two nodes where it was connected. If you had a current source, again, I'm not sure if this was ever shown قبل, بس احتياط. If you have a current source, which is usually with an arrow direction like this will become an open circuit. يعني إذا كان هني current source, you're just going to keep it open. معناتها this circuit is open at this. If you have a switch which is open, the same idea. All right. This is just the most important concept. If you don't use it this semester, you'll definitely be using it next semester in ACE circuit. All right. Since يعني all of you guys عادي نطبق نودل او مش او اي طريقه نطلع الفولتج والكرنت يعني مو لازم شيء محدد ما في اي any method you know as long as it's a correct method you guys can use anything يعني if you want to use mesh هني IA and IB you can do that it's fine but as long as you are eliminating the current if you're source sorry if you're not eliminating the source you're not using superposition anymore هو الفكرة it's to know how to eliminate the source and apply it إنزين يعني you can use that you can use current divider that I just explained you can use nodal if you want يعني which I don't recommend the fastest way is honestly using current divider and using reduction يعني reducing the circuit then it's very easy to reduce and then just applying current divider rule or the method that I usually use they don't take that much time I avoid current divider rule like I said earlier بس لأن فيها حفظ equation أنا ما أحب أحفظ equations يوم تحفظون equations تخربطون لو ما حافظينه صح فعشان كذي الفهم in my opinion is much more important than memorization. We'll take a 5-minute break خلوها 10-minute break لأن Thevenin is very straightforward التطبيق ماله it's so much easier. Let's take a 10-minute break and then I will go over the Thevenin concepts ويوم أخلص Thevenin inshallah I will look over any questions you guys might have. I will be here. I'm just taking a 10-minute break عشان مخكم انتو شوي يستوعب إذا تدورون أسئلة وهذا ونفس الوقت أحضر حق Thevenin. So break for 10 minutes and then we will continue. All right. So back at 2:10 p.m. All right, and we will start with Thevenin. If you have any questions, feel free to ask. I'll be around. You guys saw nothing, okay? You guys saw nothing. Just a quick question for whoever is here. سويتوا Norton في الكلاس ولا did he skip over it? Pretty sure you guys had to do it يعني بس سويتوه at all or Alright, if there is time, ترى Norton is very يعني it's very similar to Thevenin. They're basically the same concepts, the same idea, but one is using a current source, one is using a voltage source. That's it. If there's time towards the end of the session, I will go over Norton as well. And Thevenin is very straightforward. ما هو عادي يحل معاكم بس سؤال واحد وبعدين يقول لكم في الامتحان solve using Norton method. يسويها يعني. شوفوا when it comes to electrical the way I learned أنا الطريقة دي درستها there was not a single question on Moodle I did not solve. يعني رحت لكم حليت لكم كل أنواع circuits until I got an idea of what يعني the circuit means. And مرات they put really weird looking circuits. يعني أنتوا تتعودون على for example يعني you guys are used to looking at a circuit where the voltage source is here and then you have resistor زين وريزستور كذي. مرات ممكن يحط لكم الفولتج سورس هني زين ويحط لكم ريزستور هني ريزستور هني. So you guys need to understand what the circuit means. يعني you guys need to know how the connections are made, and the best way to do that is by practicing as much as you can. It's not enough just to focus on the theory that is being taught in class. It is not enough just solving samples, the basic samples that are given. Try to look يعني for some different questions, different looking circuits عشان you guys understand whatever type of circuit that will show up, you just understand the connection, what they mean, right? And then you can apply the basic concepts that you learn from class or from the sessions. Okay. Let us look at Thevenin. All right. So what does Thevenin يعني what was Thevenin's equivalent circuit mean? شو الفكرة من Thevenin equivalent circuit? The idea of Thevenin equivalent circuit is, let's say we have any type of circuit like this, right? Any type of circuit like this. All right, and we have a node here. Let's call this AB. This two nodes. The idea is you want to find an equivalent where you have one voltage source, all right? A single resistor here, and then that's it. So it can simplify the entire circuit so that whatever you put here, whatever load you put here, yani for example, if we call this our R load, whatever type of resistance you put here or whatever type of component you put here, you can find the voltage and the current going through it without having to calculate all of this circuit again, all right? So for example, if our load here was given, we are given our load is equal to 2.5, you can solve this using any method and you will find the current that is going through our load and the voltage at our load or the voltage drop because of the load R. But what if I tell you, okay, now I want it to be 17? You're going to have to solve it all over again from the beginning to find our load and all of that and current, and you can do that. But the idea of doing the equivalent circuit is that you can put any resistance at any time, يعني you can change it. This symbol, by the way, is for a variable resistor. معناتها resistance you can play with it. You can make it 2.5, 7, 16, 2. يعني you can change the resistance at will at any time. All right? So the idea is to find an equivalent circuit where this is V Thevenin. This voltage is going to be the Thevenin voltage, and this is going to be your R Thevenin. So this is a specific resistor, which is an equivalent to all of this. And this is a specific voltage, which is equivalent to the voltage source there. And then using this simplified circuit, you can easily find the current going through RL using basic V equal IR equations. And you can find also the voltage across A. But how do we do that? So the very first step, step 1, we need to find R Thevenin. All right. To find R Thevenin, we need to remove sources. So if we have any voltage source, if we have a voltage source, this is going to become a short circuit. All right. And if we have a current source, this is going to be an open circuit. Okay. Again, we're dealing mostly with voltage sources so far. That's all I've seen. So we're just going to just remember that voltage sources are going to become shortened. So if we take this circuit again, all right. First, we remove our R load. We don't care about our R load. The idea is we're going to have two nodes here. This is where we're going to be connecting any component, all right? And we're going to be removing our voltage source. Since it is a voltage source, we're going to be shortening the circuit. Remember that we are looking at the circuit from this side, at A and B, all right? Because here, as if we have a voltage here, or as if we have a voltage source over here, or whatever, and then just basically think of it as if you have A to B, you are finding R Thevenin from this point of view. معناته, if we look at the connections now, we see that this and this, these two are in parallel because they're connected at 2 points, and they are in series with the 15 ohm resistor. So how does that work? R Thevenin is going to be, so since these two are in parallel, 6 times 9 over 6 plus 9, and the 15 ohm is in series, so it's plus 15. This is our very first step. We find our R Thevenin. So R Thevenin is going to be equal to 6 times 9 divided by 6 plus 9 times, plus 15, which is going to be 18.6 ohms. All right. So this was our first step. We found our R Thevenin. Second step, step 2. Step 2 is, first we found our R Thevenin. Now we need to find our V Thevenin, the voltage that we have to put here. All right. So how do we do that? So first, let me just copy paste the circuit one more time. So now we need to find our V Thevenin. Okay. To do that, again, our R load, we are removing it. We just have our two nodes A and B over here. And we can use any method to determine our V Thevenin. So what is V Thevenin? V Thevenin is basically the voltage that is going across A and B. So it is VAB, all right? This over here is V Thevenin, all right? The voltage that is across A and B. So if you remember, if we look at the equivalent circuit, V Thevenin is going to be the voltage that is going between A and B, all right? This is the whole point. So how can we find that? So first of all, we need to find out, there are different ways you can look at it. There are multiple different ways you can look at it. So we know, if you remember, if we had something like VAB, we use something like KVL to go from B, all right, all the way to point A. We're going to go all the way across here to reach the V Thevenin to find out what the voltage of V Thevenin is. Okay, that is how you can simply find the voltage across V Thevenin. Another way is, in this case, because it is a simple circuit, remember, this here technically is open. For now, it is technically open when we are trying to find V Thevenin. So we know that this voltage over here is all the same. All right, يعني الvoltage هني V is equal to the voltage of V Thevenin because there's no voltage source here or anything. There's just a resistor. But since there's no current going through this resistor, there's no voltage drop. There is no current here. It's an open circuit. There's only current going here. So we can say that this, we don't look at this resistor. We could just say this is V, which is equal to V Thevenin. So if we call this V, this V Thevenin is also equal to V. So you can find this V, which is also going to be V Thevenin. Again, this is depending on how you want to look at the circuit. All right. So if we want to use this method, all right, if we want to use this method first. So we want to find our V. How can we find V? There are so many different ways you can find V, but the easiest one is by just applying KVL along this line. So let's call this current I, because this is the only current. Remember, this is an open circuit, all right? So to apply KVL, remember, we have our polarities. So since current is going in this way, this is going to be plus minus, this is going to be plus minus. KVL, we have our 10 volts, so it is going to be plus 10 volts because current is going upwards. Current is going in that direction. It is going from minus to plus, so it's a gain, so it's positive. Okay, so plus 10 minus 6 times I, V equal IR, remember? So it's just 6 times the current, 6 ohms times the current, minus 9I. And this is all going to be equal to 0. All right, just applying KVL. Again, we start from a point. We go here, we have voltage gain. We have voltage drop due to the resistor. We have voltage drop due to the resistor. And then we finish our loop. This is how we apply KVL. All right. Now we can solve and find our current I. So if we want to solve this, we're going to get 15I is equal to 10. So I is equal to 10 over 15, which is 0.67 amperes. Okay. So now that we found our current, well, the idea is we are trying to find voltage V. Why did we find the current? Because now we know that this is our ground voltage. All right, this is V0 equals 0. We know that VR, let's call it V9 or VR9, okay, which is the 9 ohm resistor. It's equal to I times 9 ohms. And we know that the current is 0.67 times 9. So we can find out that VR9 is equal to 0.67 times 9 times 9. It's going to give us 6 volts. Okay? So we found that VR9 is equal to 6 volts. So VR9 is also equal to the V voltage minus V0. If you look at this, it's V on the positive side. All right, so V is on the positive side. Oops. Second. So V is on the positive side, and on the negative side is V0. So it is going to be V minus 0. So it's simply also equal to, V is equal to, I should say, also 6 volts, because VR9 is equal to V. And that's how we found our VThevenin, because earlier we have already determined that VThevenin is equal to V. Again, the reason VThevenin is basically VAB, all right? It's the voltage at A, okay? So the reason VThevenin is equal to V is because there is no current flowing through here, all right? There's no current flowing through here, or assumed to be no current when you're trying to find VThevenin, all right? So this resistor has no effect on the voltage. There is no voltage drop due to this resistance. Therefore, V is going to be equal to VThevenin. The voltage here is all the same. Okay, this is the whole idea. So now we have found our VThevenin, which is equal to 6 volts. If you notice, if you use the different method, which is always, this is basically a shortcut method, you can say, when you have a simplified circuit. Let us use the actual method that will be applied for any type of, like if you have any type of circuit and you're trying to find VThevenin, the actual proper way, okay? So, let me remove the ground, let me remove this. So we know that VThevenin is equal to VAB, all right? If you understand this, you're going to be able to solve any type of circuit that is, any type of Thevenin circuit that you need to do, okay? So what does VAB mean? It means we need to find the voltage starting from B going to A, all right? So we need to find going from B to A. So let's start from B going up. Okay, so going from B to here we have a voltage drop. The same idea of KVL, if you remember, that we used to apply. Here we have a voltage drop. What's the voltage drop? It's equal to I times 9 ohms. And it's not a voltage drop in this case because we are going from minus to plus. We are going from minus to plus. So it is a gain, actually. So it's going to be positive I9. And if we keep going up, we're going to A, right? This is the path we are taking. So in this direction, we're going in this direction up to A. Remember that this resistor, there is no current flowing through it in this case. Therefore, there is no voltage drop due to this resistor. Okay? And this is VThevenin, right? So this is going to be, so VAB is equal to simply plus I9 ohm. In other words, VAB, we found the current earlier, all right? We found the current earlier. So it's 0.67 times 9. So VAB is equal to, if you notice, the same exact equation, which is 6 volts. So this is equal to our VThevenin, all right? Again, what we did is we followed the path. We start from B going to A because that's what VAB is. VThevenin is simply the voltage across A and B. So we go from B. We have a voltage gain here because we're going from minus to plus. So this voltage gain is simply I times 9. And then we move here going to A. Since we have no current flowing through here, since this is open, theoretically open, I should say, ما عندنا current, so this resistor has no voltage drop or gain effect. And then we found our VAB. We reached our node A. So this is how you find VAB. This you will apply to almost any type of circuit you have. And we'll see an example where we don't just have a resistor here, we have also a voltage source. عشان you guys just understand how you will be applying it. So now we found our VThevenin to be equal to 6 volts. All right, that was our second step. So step 1, recap, is R Thevenin. We remove the sources and find R Thevenin from AB. And now step 2 is finding VThevenin, which is simply the VAB voltage. All right. Now that we found this, step 3. All right. Step 3 is equivalent circuit. خلصنا. Since we found VThevenin and R Thevenin, we can now draw this circuit, the equivalent circuit. So the equivalent circuit is going to look something like this. Resistor here, which is R Thevenin, node, and the second node. This is A, This is B, open nodes, all right? And we can connect anything to it. So this is R Thevenin, which is equal to, we found earlier to be 18.6, I believe. And plus minus, this is VAB or V Thevenin, which is equal to 6 volts. And this is our equivalent circuit. Now, let's say we have a load, all right? So we have a load. We can attach any load across this AB and we can find out the current that is going through it or the voltage drop across AB, okay? So let us attach a load like that. Our load, let us assume that it is 2.5 ohms, all right? Now you can find, how can you find current? First of all, this is a series circuit. So current flowing through all of this is the same. This is the whole point. So we know that I, let's call it I total, is equal to V Thevenin over R plus R load, because this is R total, which is R Thevenin plus R load. Because R total, they're in series. These two resistors are in series, so you just add them up. And that's it. And now you can find IT is equal to V Thevenin, we found was 6. R Thevenin is 18.6, and R load is 2.5. Put that into the calculator. So it's 6 over 18.6 plus 2.5. This is going to be 0.28 amperes. And this is the whole rule for Thevenin. This is the exact same way. A quick recap. The first step you will do, all right, step 1 is finding R Thevenin. How do you find R Thevenin? You have to remove the sources and then you have to look at it from the nodes at which your load is supposed to be, okay? So removing sources, if you have a voltage source, it's a short circuit. If you have a current source, it's an open circuit. In this case, we had a voltage source here that we shortened. These two are in parallel, and they are in series with this. And we found our R Thevenin, our equivalent resistance, which is our R Thevenin. Second step is finding our V Thevenin, which is simply VAB. You're going to have to find the path here, all right, and find anything that is along this path. So we have the resistance here, but we don't have the current. You can find the current using any method you want. The easiest one here is just KVL, because we have a single current only. So we can just do KVL to find the current. We apply KVL, so it's plus 10 minus 6i minus 9i equal to 0, all right? And then you solve for I. Now we have our I9, our current that is flowing through here. Since we are going upwards here, when we're going from B to A, because remember, VAB means we are going from B to A, all right? I'm actually going to write that down. So it's from B going to A, all right? So, again, you just are going to follow from B to A. We are going through this resistance from minus to plus. Polarity is always important, from minus to plus. So it's a voltage gain. So it's going to be plus I times 9 ohms. And then we're going through this. Since there is no current flowing through this resistor, it is going to be assumed to have no voltage drop. So there's going to be nothing here as well. And then we reached our point A. So VAB is simply equal to this. And this is also our V Thevenin. Now that we determined V Thevenin, R Thevenin, we can just simplify the circuit and have it here. And you can put any R load. If you notice now, if we changed our R load to any value, let's say it is 10 ohms, all you have to do is just change this value to 10 ohms. And you can solve for any type of current, no matter what the load is. Remember, this is just an equivalent of this circuit. يعني هني بعد, if we change this to 10 ohms, the value there is correct. This is your I total for the circuit. Okay, or we should technically call it I load. All right, this is our I load. So I'm just going to write it here, I load. And this current over here is I load. Because it is a series circuit, the current is the same everywhere. So instead of IT, let me just call it I load to avoid confusion. This is the current that is flowing through the load. Is it clear? So let's solve this question. Any questions, please ask now before I go into this question, because I want to go into this question and then I'm going to explain Norton very quickly as well. So we have a voltage source, we have a resistor over here, we have a resistor over here, we have another voltage source down here. Okay, we have another voltage source down here. Then we have a resistor over here. Then we have another voltage source over here. Then we have our Then we have our load. So this is our node AB. This is A. And this is B. And this is our R load. Okay, R load. This is plus minus, and plus minus. All right. So we know that V1 is 20 volts. We know that V2 is 15 volts. And we know that V3 is 5 volts. All right. And we know that R1 is 230 ohms. R2 is 250 ohms. And this is 350 ohms. Tamam? And our load is given to be, our load is 1050 ohms. Okay? So this is the circuit we have. Again, go step by step when you're trying to find the equivalent. So equivalent, you know that your node A and B, if you notice I wrote it directly here, it is always going to be where your R load is. So here, if you notice, our load is over here. So we know that this is our A and B nodes, okay? So it's exactly where the R load is connected to, tamam? So this is where our A and B is. Step one was finding our Thevenin. To find our Thevenin, we need to remove the voltage sources and shorten the circuit. So voltage source, and voltage source. Remove our R load for now. And then this is going to be a shortened circuit, and shortened circuit. Okay. I'm just going to write SC, so you guys understand that this is the place where we shorted the circuit. Again, to find our Thevenin, we're looking at it from this direction, our Thevenin, as if there's a voltage source here. And then, again, this and this, these two are connected in 2 points. So these are in parallel with each other, and they are in series with this circuit. So our Thevenin is 230, or resistor, I should say, or 230 times 250 over 230 plus 250 plus the 350 ohm resistor. So our Thevenin is going to be equal to 469.79 ohms. All right, so we found our Thevenin. Easy. Our Thevenin, I'm pretty sure all of you find it very easy. Now, let us find step 2. What is step 2? This is step 1 complete. Let's go for step 2, finding V Thevenin, which is equal to VAB. Okay, let us remove this again. So if you notice here, we no longer have a simple circuit anymore here. We have a resistance and a voltage source as well. So we cannot apply the V over here and finding it. Yani we cannot do V and this is equal to V Thevenin anymore because we have a voltage source. Technically, you can say that there is a V here and there is V Thevenin, and then you subtract or add the voltage source here depending on polarities. But that gets very confusing over time. So the easiest way to do this is doing VAB. But first, if we do VAB, so VAB again, VAB, all that means is going from B to A. All right. So let us do that. So going from B, from here, all the way to A. Okay. First thing, we need to identify a current flowing in this direction so that we know the polarities of the resistors. Let's identify current going in this way. This is current I. So this is going to be plus minus. This is going to be plus minus in that way. Okay. So if we apply the KVL rule for VAB, we know that VAB is going to be equal to, let's go step by step. So we're going in this direction, We have a voltage gain because of the voltage source. So we have plus 15 volts, all right? This is due to this voltage source over here. It is a gain going from minus to plus, so it's a gain. After that, we're gonna look, if we keep moving forward, we go up here, we're gonna have this resistance, and we're going from minus to plus, so it's also a gain. So it's gonna be plus I times, what's the resistance? 250 ohms. If we keep moving forward, again, there's no current flowing through this. Theoretically, there's no current assumed going through this resistor, so it has no effect. But we do have a voltage source here, and it is plus minus like this. Since we're going from plus to minus, it is going to be a voltage drop. So it's going to be minus 5 volts. And this is our VAB. What do we need to determine first? We need to determine our current I over here. This current, we need to determine it. Since we don't have it, current I, which is this current I, so we can simply just apply KVL to find it. If we do KVL to find I, let's start from over here. All right, let's start from over here. Oops. Let's start from over here. If we go up, we're going voltage gain from minus to plus of 20 volts, so plus 20. If we keep moving, we go over here, plus minus, it's a voltage drop, so it's minus I times 230 ohms. And we keep moving, going into this direction. Again, another resistor from plus to minus, voltage drop. So it's minus I 250. Again, we keep moving. We're going here from plus to minus. We are going from plus to minus. Another voltage drop due to the source. So it's going to be minus 15 volts equal to 0. Tamam? Simplifying this, we can find I. It's going to be 20. So it's going to be 480 times I is equal to 5. معناته I is equal to 5 over 480, which is equal to 0.01042 amperes. All right? Or for 10.42 milliamperes. Tamam? Again, we're not going to look at milliamperes when solving. We're using amperes always. Now that we found our I, we can now just plug it in back into this equation over here. So if we plug it in back into this equation, remember that this I is the same I, all right? So this value, we're plugging it in back, oops, not the in milliamperes, in amperes. We're plugging this in back the equation to find VAB, which is Thevenin. Remember, VAB, this is equal to Thevenin. So Thevenin is equal to 15 plus I, which is 0.01042 times 250 minus 5. Okay, so Thevenin is going to be equal to, putting that into the calculator, 12.60 volts. And that's it. Now we can draw our equivalent circuit. We have our Thevenin, and earlier we found our Thevenin, which was equal to 469.79. 469.79. All right. See, if you follow for Thevenin, if you follow this rule going from B to A, it is always going to be simple, no matter what voltages are given here or what sources are given, all of that. It's going to be very simple as long as you just know how to follow the path properly. Tamam? So R Thevenin and V Thevenin are given. If we want to draw our circuit, this is going to be plus minus going up. We have our R Thevenin over here. All right, and we have our node A and our node B. Okay, this is A and this is B. So our Thevenin, which is 469.79 ohms, and this is 12.6 volts. Okay. Now, whatever the load that we are applying here, we can find out the current that is flowing through it very easily. So remember that current here is all the same, which is I load current, all right? It's all the same because it is a series circuit. So I load, we were given that our load was equal to how much? 1050. 1050. So I load is equal to V Thevenin over R Thevenin plus R load. All right. Again, the idea is this is just because they're in series, so you're just adding these two together. All right, to find the total resistance, which is R Thevenin, and this is R Thevenin, and this is V Thevenin. All right, so R Thevenin, you're adding it to R load to find the series equivalent, and then you're dividing the voltage on top of them. معناته I load is equal to 12.6 over 1050, or I should say 469 أول شيء R Thevenin 469.79 زائد 1050, and you'll find out that your I load is equal to 8.29 milliamperes, or 0.00829 amperes. And that's it. This is how you solve any Thevenin circuit. Is it clear? Any questions about Thevenin? Okay. Okay then. So this was for phi Thevenin. Again, you can solve for I in any way you guys want. Yani here it is a very simple circuit. That's why KVL is the easiest way to go. All right, you can solve for I in any way you want. The solving isn't yani the reduction and all of that. You just have to follow the steps and doing it the same way. And then when you come to solving similar to superposition, you can solve in any way as long as you're applying the same concepts that you were taught earlier. Tamam? Let us look at Norton very quickly. Let us do a very simple circuit. عشان بس I explain the concept. The very first circuit I did, where was it? حق R Thevenin. عشان I related to R Thevenin. So we found out that this circuit, let me just copy paste this down here. Zain. So this is now we're looking at Norton. Okay. So first things first, for Norton, our circuit, our equivalent circuit is no longer going to be a voltage source. It is going to be a current source. All right. So there's going to be a current source, and our resistor is no longer going to be in series. Our R Norton, it is going to be in parallel. And then you have your A and B over here in parallel. All right. This is the difference between Thevenin and Norton only. All right. So this is going to be I Norton. You're going to have a current called I Norton, and you're going to have your R Norton over here. One thing you should know, R Thevenin is equal to R Norton. Always. This is always the case. Your Thevenin equivalent circuit, the resistance of it is equal to R Norton. Tamam? Again, here you're going to have a load, whatever the load is, R load. All right. So if you notice now, you have different currents going through R load. Like R load is not the same as I Norton because they're in parallel, so the current is different. However, the voltage is the same here. The voltage is the same across everything because it is a parallel circuit, and that's the whole concept of why we use Norton over Thevenin. In practical applications, if you're trying to find voltage drop, you will apply Norton because here voltage is equal everywhere. Yani voltage here is all the same. All right. And this is our ground. So this is 0. Okay. So the voltage is the whole all the same here. In Norton, if you remember, the current is all the same. So if you're trying to find the current going through the load, most of the time you'll be using Thevenin. And this is in real life examples. Obviously, here you can find both using both ways. All right. So we're just going over the concept. Now, I'm gonna start with. I'm not gonna show you the steps of finding Norton first. I'm actually gonna compare the Norton to the Thevenin circuit. The first thing you need to know, so since R Thevenin is equal to R Norton, and then since R Thevenin is equal to R Norton, let us look at our Thevenin equivalent for this circuit. Where was it? I drew the Thevenin equivalent earlier for the circuit. This was our. So this, yes. Was it this? No. 1 second. Okay. So this was our Thevenin equivalent for the same circuit. Tamam? This was our Thevenin equivalent for the same circuit. Okay. Let me copy this down here and we'll put them side by side so we can compare. Okay. So I've already found the V Thevenin. Okay. We're not looking at our load. We don't care about the value. We found our R Thevenin earlier, which was 18.6. So we know that R Norton is also going to be equal to 18.6 ohms. Okay. So as you can see, step 1 for R Thevenin or R Norton is going to be the exact same thing. You're going to be eliminating your sources to find R Norton or R Thevenin because they are equal. So it's the exact same first step. And another important thing you need to know is that V Thevenin is equal to, before that, remember that V is equal to I times R. All right. In this case, V Thevenin is equal to I Norton times R Thevenin or R Norton. It doesn't matter because they are equal. So this is another thing. The current that you have that is flowing, that is used, the current source that is being used over here is going to be equivalent to your to the voltage drop due to the R Thevenin resistor. All right. This is an important relation you guys can use because this way, if you solve using Thevenin method, you can find your equivalent I Norton instantly. So for example, for this circuit, if we want to find I Norton now, we know that V Thevenin is equal to 6 volts from our Thevenin circuit, and we know that R Thevenin or R Norton equal to R Thevenin, which is equal to 18.6 ohms. So if we want to find I Norton, it is simply V Thevenin over R Thevenin. All right, which is equal to 6 over 18.6. So I Norton is equal to 6 divided by 18.6, which is 0.323 amperes. If you notice, خلاص, now we can build our I Norton circuit very easily because we have our current source. Remember, a current source, right? No, the arrow should be in the opposite way. So our current source, you're going to be having a current instead of a voltage. That's the whole idea. And usually a voltage source, you're writing V is equal to. But in current source, you're going to be writing I is equal to. So in this case, IN is equal to 0.323 amperes. And remember, in Norton, we have a parallel circuit. This is our node A, our node B, node A and node B. And this is our R load. All right. So this is R Thevenin or R Norton, which is 18.6 ohms. All right. This is R Norton. And you have your circuit. Current source basically means that this current over here, this is your IN. This is your I Norton current. And then your I load is going to be over here. This is your I load. And this is the current that you're trying to find. Okay. Now, how do you find the current here? Again, you can either use voltage divider rule or the method that I usually do. Since these are in parallel, you can easily use, current divider rule. If you use current divider rule, I load is going to be equal to I Norton times Remember, it's going to be the other resistance, so it's going to be R Norton over R Norton plus R load. And you can find your I load directly, all right? Or you can use the same method that I usually do, which is V up, V down, all of that. But when you're using Norton method, it's a very simple circuit. That's the whole idea. It's very easy to apply current divider rule to find out the current that is flowing through I load, all right? So this is how you can equate, or you can relate, I should say, a Norton to your Thevenin circuits. All right, they are basically the same exact concepts. The only difference is one, you have a current source, the other, you have a voltage source. And the current source, you're having a parallel circuit, and for a voltage source, you're going to have a series circuit. Tamam? If you want to solve it from zero, and if you want to go follow the steps, for the exact same circuit, let's do the same thing. Okay. So step one, find R Norton, which is equal to R Thevenin. Keep that in mind. All right. To do that, it is the same step that we applied here. Step one, remove sources, plus minus for voltage sources, short circuit, for current sources, open circuit. Since we only have a voltage source, basically we are just going to be repeating the same step that we have applied, but let me just copy paste this down there. All right. So step one is the same as the Thevenin one, so I'm not going to apply it again. All right. So step one, same as Thevenin. All right. Since we're doing it for the same circuit, we found out that Rn is equal to 18.6 ohms. Okay. The same method. You're going to remove this. You're going to find the voltage, the resistance equivalent for the circuit, all of that. Step two. Now, since we are trying to solve it using Norton, we need to find our I Norton. All right. Now, this is very important. So we have this as our circuit, right? This is the original circuit. Let me actually keep it as it is. And then, so step two is going to be finding I Norton. Remove the load again. The difference in step two, remember for V Thevenin, what did we do? We left AB as an open circuit, all right? We left it as an open circuit because we were trying to find the voltage. For Norton, we are going to be doing a short circuit here. This is the main difference between I Norton and V Thevenin when you're doing the steps. So for I Norton, you're going to short AB, all right? You're going to be connecting a line, and the current going through this is going to be your I Norton. Tamam? This is the way you will be finding your I Norton. Again, the method you want to use to find I Norton can be any way. Yani, for example, I'm going to use mesh, for example, all right? Even though it's pointless, but I'm going to say that this is I1 and this is I2. All right, because now there is a current flowing through here, the I Norton current, because we shorted the circuit, theoretically, al-aqal. Or you can also apply, by the way, current divider rule, which is the same thing. But I prefer to use this. So if we use mesh, if you remember mesh, KVL for both circuits, and so I1, if we just apply for first loop like this from here, so we're applying KVL, and then we're going in that direction. So it's going to be plus 10 polarities. This is going to be plus minus for the first loop. For the second loop, this is going to be plus minus and plus minus in that direction. Okay, so it's going to be plus 10. This is for loop I1, or let's call it IA, since we usually call them IA and IB. All right, this is IA and IB. So loop IA plus 10 KVL plus 10, and then we're going to have a voltage drop of minus IA times 6 minus IA times 9 voltage drop for this. However, since we have also IB going upwards, so it's plus IB because it's a voltage gain times 9 equal 0. So if we simplify this, grouping up the IA, it's going to be minus 6 and 9, that's 15 IA plus 9 IB is equal to minus 10. Again, I'm only using this method to show you that you can use any method to solve for the currents. And then, so IA, this is our first equation from the first loop, right? This is equation 1. And then, now equation 2 is going to be from loop IB. Again, we're applying KVL. Loop IB, if we look at it here, let's start from anything. We can start from down to up, yani. If you want, we can start from B going like this in that direction. All right, so starting from B, we're going to have a voltage drop due to 9 to the 9 ohm resistor. So it's going to be minus IB times 9 plus IA, because IA is in the opposite direction, times 9 minus the drop across the 15 ohm resistor. So IB times 15 equals 0. Again, rearrange, it's going to be 9IA minus 15 minus 9, that's, or minus 15 minus 9, that's minus 14, 24. Minus 24, IB equal 0. Get the calculator, mod 5, 1. And then, this is our equation 2, all right? Mod 5, 1. Okay, you're going to find out that IA is equal to something and IB is equal to something. So minus 15, 9, minus 10, and 9 minus 24, 0. So I get the X value, which is IA, is 0.86 amperes, and IB is 0.32 amperes. All right. Again, since they are positive, معناته the assumed directions are correct. يعني the loops are correct directions. Remember, all we care about is to find IN. So you see IN is basically equal to IB because they're both in the same direction. So IN is equal to IB, which is 0.32 amperes. And this is your IN value. And if you notice, this value, 0.32, this is the exact same value we found earlier for IN using this relation. 0.323, I put an extra decimal place, but this is the same current that you found. And then step 3 would be building the circuit using IN and your equivalent resistance. And this is how you apply Norton method. So the only difference between Norton method is step 2, you're going to be shortening the circuit from A to B, and you need to find the current going through it. And Thevenin, you're opening the circuit, and I'm going to mention that as well in the notes. All right. So VAB, and here you're going to be opening A, B, the nodes A, B. All right. And then you're going to be finding the V Thevenin at point A. All right. You're going to be finding VAB basically. That's the only difference. And then the circuit for here, it's going to be a series circuit with R Thevenin, and for Norton, it's going to be a parallel circuit. And you can see that if you find one of them, you can simply find the other one directly without having to go through all of this. And that's pretty much it for Thevenin and Norton. I hope this session was helpful. And if you have any questions, feel free to ask.